Day 144, Physics, Circuits, Problem 1D. Once again, applying the basic principles. We're going to be drawing new diagrams, applying these two principles for parallel and series. And as I said before, you don't always start with the parallel part or the series part. Sometimes all you have is parallel, all you have is series. Here we have a combination of parallel and series. The question is, where do you start? And hopefully after a lot of practice, you'll figure out where you start. In problem A, I think we started with the series part of the circuit. Here, like in part C, we start with the parallel portion. The 20 and the 10 are in parallel with each other. There are two different pathways to get, I'll label these, from this point right here. Let me call that point A, sorry with the big blob. That's point A, and then point B over here. That's point B. All right, if you're at point A, there's two ways to get from A to B through the 20 and the 10. So they're in parallel. I'm going to combine those by 1 over our total equals 1 over 20 plus 1 over 10. I'm going to do the calculation there and then draw these diagrams. So when I did the calculation, we end up with 6.7 ohms of resistance when you combine the two parallel 20 and 10 ohm resistors. So I drew the new diagram, 6.7 replacing the 20 and the 10. And now I see that these two are in series, the 30 and the 6.7. Combined, just add them, 30 plus 6 is 36.7. So the final diagram looks like this. 100 volt battery, 36.7 ohm resistor. Then I use this final simplified diagram once again, and I apply Ohm's law working backwards. So I'm going to simply be using V equals IR from now on, starting with the simple diagram, going to the middle diagram, then going back, way back to the first diagram. But I have 100 equals I times 36.7. I is 2.7 amps. So the battery is pushing 2.7 amps. It's everywhere in the circuit. It's flowing, say, around like this. 2.7 amps of current. So if I go to the middle diagram now, it means the same thing here. This is one single loop. There's 2.7 amps of current. In series, these two resistors are each receiving 2.7 amps, 2.7 coulombs per second. They do not have the same voltage. They have the same current. They're in series. The rule is in series you have the same current. You have to calculate their voltages. So the 6.7 ohm resistor, I'll do V 6.7 equals its current times its resistance. I don't know what its voltage is. I'm going to figure that out. It's the current of 2.7. It's 2.7 times its resistance of 6.7. So the voltage for the 6.7 ohm resistor is 18 volts, not 100 volts. For the 30 ohm resistor, the 30 ohm resistor will be its current times its resistance, so V30. The current through that is 2.7. Its resistance is 30. So the voltage for the 30 ohm resistor, 2.7 times 30, is 81 volts. In a perfect world, that would have come out to be 82, because 82 plus 18 would be 100. They should be close to, they should add up exactly to 100, but because of round off, once again, it's close, 99. All right. So I keep going back to the original diagram and use V equals IR. I have two resistors left in the original diagram. I have the 20 and the 10. So they're in parallel. They have the same voltage. The question is, what is their voltage? They have different currents. They have the same voltage, but it's not 100 volts. What is it? Well, their voltage is the same as the voltage of its replacement, which is this over here, the 6.7. The 6.7 ohm resistor over here in the middle is 18 volts. I'll write that down in green. 18 volts for that 6.7 ohm resistor. So each of those is 18 volts. 18 volts. Oops, I don't know if you can see that too well, but they're each 18 volts. The same voltage, not 100. They share the same voltage. It's the same voltage as as the replacement resistor, the 6.7 ohm resistor over here in the middle diagram. So now I use Ohm's law on that resistor. So, or each of the two resistors. So, for example, for the 10 ohm resistor, V10 equals I times R for the 10 ohm resistor. Its voltage is 18. I'm looking for the current because they'll have different currents. More current in this resistor. It's a 10 ohm resistor. Its current in the 10 ohm resistor, that should say 10 right there, I sub 10, is 1.8 amps. That says 1.8 right there. If you can see it too well, 1.8. The 20 ohm resistor is basically going to have half that current. I can do the calculation though. So V20 equals I times R for the 20 ohm resistor. I know it's got 18 volts. I'm looking for I. R is 20 ohms. So you do the math there. The current I20, the current in the 20 ohm resistor, is 0.9 amps. Another check on that, if I add 0.9 plus 1.8, I get 2.7 amps of current, which is what we have in the final circuit, because the two currents through those two branches have to add up to the current that comes out of point B and goes through the 30 ohm resistor. Now I can fill in my chart and just pick numbers out. So the 10 ohm resistor we just figured out is 1.8 amps of current, a voltage of 18 volts. The 20 ohm resistor is 18 volts, same as the 10 ohm resistor, and its current was 0.9 amps. 30 ohm resistor had a current of 2.7 amps. If you look at the diagram, you can pause and look at that if you want. And it has a voltage in black towards the bottom right here, 81 volts. The battery was supplying 2.7 amps. All of that is split between the 10 and 20, but then comes back together, goes through the 30 ohm resistor. It has 100 volts. And then you multiply voltage times current once again, V times I, to get the final column. I'll do that. So I've done the calculation on the power. And if you look over there, once again, if you do a check, the power that's supplied or used up by the resistors, light bulbs, those three powers should add up to 270. It's real close. They add up to 260 something, 267, rounded off to 2 sig figs would be 270. The battery supplies the energy, 270 joules per second, and the bulbs turn it into light and heat at those respective rates, and the 30 ohm bulb would be the brightest, 219 watts.